Here's something really important in probability and statistics. It's this notion of convergence in distribution or convergence in law. Same thing. Okay, so the sequence of random variables x1, x2, x3, x4, etc. converges in distribution, is what we say. This sequence converges in distribution or converges in law to the random variable x if the sequence of CDFs converges. So n goes to infinity to the CDF of x. Pointwise, everywhere where the CDF of x is continuous. So remember, in general, CDFs don't have to be continuous. They can have those jump points. Okay, so this is sort of a weak form of convergence, but it's really nice because sometimes we often deal with sequences of random variables, and we want to know, is maybe n is time as time goes to infinity, or maybe we're talking about a sum of these random variables, and n is the number of them. Is the number of those things goes to infinity? What is the collection of these things? What is their sum, or is whatever you want to call it? As n goes to infinity, can we approximate the behavior of this kind of random variable with something that's maybe a little more tidy, something that's easier to deal with? Okay, and so so there's another little theorem that lets us do that. It turns out there are all kinds of transformations in probability and statistics that are useful. This course focuses on the moment generating function. There are also Laplace transforms and Fourier transforms, or characteristic functions. There are probability generating functions, and you'll see all these if you take some more probability. But for now, we'll just stay with the moment generating functions, and so we have a nice little theorem here that says that if moment generating functions we'll call them m sub x sub n of t are defined and if the limit as n goes to infinity of these moment generating functions is the moment generating function for this other variable x, then the xn converge in distribution to x. Okay, that's a much easier way to deal with convergence in distribution, or to prove convergence in distribution, rather than dealing with their cumulative distribution functions. And also, by the way, sometimes we denote convergence in distribution by this. We might say that xn, the sequence of those guys, converges in distribution to x. Okay, so arrow meaning converges, d meaning distribution